Welcome class, this is going to be our last example on the light board for now. We'll see if we get the opportunity to keep rolling with these videos. If you like them too, I'll make sure I'll pass a poll. So this very last one is going to be about the Bernoulli equation. So as you can tell, the Bernoulli equation applies under certain cases only. What we have here is a water reservoir. So we have like a big water tank that is pressurized. It has 60 psig. And this water tank will have a hose connected all the way to the bottom coming up. And then you have a nozzle. Imagine you store water from rain. And then you add air to pressurize the tank to just water your lawn. Things like that is something you can do. So what we're going to calculate here is what is the velocity of the water flowing out of the nozzle that we have right here, assuming that it is frictionless. So one thing we want to calculate here is what is that distance. So that distance is going to be 30 feet from where we have the pressurized line to where we have the nozzle exit. So that's, I don't think that was given in the problem statement, but that's the height difference. So now we're going to write that Bernoulli equation. So what we have for Bernoulli is going to be delta P over rho plus G delta Z plus delta U squared over 2 equals to 0. Notice here, this still has units of meter squared over second squared. If you divide by the gravity, then you get the head equation. So now let's simplify the del terms. So what we have is P2 minus P1 over rho plus G C2 minus C1 plus U squared at the exit minus U1 squared over 2, and this is equal to 0. What we can simplify here is, let's go back to our figure. We have 60 psig over there. So it will be important here to note where is your point 1, right? So right there, that is where I will have my point 1. So that will be my pressure 1. Now to identify the point 2, that will be right there at the top. That's going to be my exit point. So if you notice, this nozzle is discharging to atmospheric pressure. So notice how inside the tank I have a 60 psig. So what that means is that I can use gauge pressure, right? Whenever you have a manometer. So the P2 to the discharge will be equal to 0, considering a gauge pressure. Now, what happens if you consider atmospheric pressure? Well, if you consider the atmospheric pressure, you got to make sure that you add that value to the 60 psig here that you have in the tank. So we're not doing that. We're just considering P1 to be equal to that 60 psig. Now what about C2 and C1? Another important parameter there as well, right? We have the total difference, so I'm just going to keep that as the 30 feet we have. And then we have U2 squared minus U1 squared. A big assumption that we will make here is that we know this velocity, that's what we're trying to find. But inside the tank, we're going to assume that this area is so large that the velocity can be considered negligible. So what that means is that U1 can be approximately equal to 0. So remember, we're trying to find what's that U2 square value. Let's calculate that component here. U2 square will be equal to, notice I got a negative P1 over rho. So when you move it to the other side, it will become positive. You have a plus G delta C. I have to put a negative G C2 minus C1. And this whole term is going to be multiplied by that number 2 that we had in the denominator before. So looking at this now, we're going to look at putting the numbers, right? So let's estimate with the square root of all this, we should be able to get the correct value. So I'm going to calculate the square root, and let's put that 2 outside. Let's move it to the front so we avoid any confusions. Now, pressure, the initial pressure at the tank was given as 60 psig. So 60 psig is going to be 60 pound force over inch square. When I divide by the density, that is going to be 62.4 pound mass over cubic feet. And then you're wondering here, right, these units do not make a lot of sense. We're working in the English system, so we need to multiply by that lovely GC factor, 32.2 pound mass, foot, pound force, second square. So that will help a little bit. We can calculate or get rid of the pound force, the pound mass, but still we have some inches square in here that should get canceled, right? So we're going to change that inch square to foot square by doing this other factor. And lastly, we have still the gravity term. If you recall, the gravity in English units will be 32.2 feet per second square, multiplied by the C2 minus C1, which we know is 30 feet. Okay, so with this, we can just calculate what is going to be the U2 value right at the exit. So let's calculate that velocity at the outlet, right? So we pretty much have everything here. You can see all the units will make sense. Let me clarify here. Pound force will cancel here. Pound mass as well. And then you have that inch square canceling here. That ultimately will give you those feet square over second square. That's what you're looking, right? So when you take the square root, the final velocity will be in terms of feet per second. So when we do that calculation, I get a value of 83.6 feet per second. Make sure that you're doing these calculations with me. If you find any mistakes, kindly let me know. So we're going to change this to something that we know, right, like meters per second. So 12 inches is going to be 1 foot. And then we also know 2.54 centimeters or 0.0254 meters are 1 inch. So the final answer that we're going to get here is 25.5 meters per second, which is quite intense, right? What you get from that nozzle if you're watering your lawn, right? So you can see how you can put some pressure in a tank and get good enough flow rate coming out of the system.